So we're now on to the second law of thermodynamics, and before talking about it, I just want to put it in a little bit of broader context. So here's a picture that you may have seen in a mechanics class, for instance. And probably the best thing to do is say it out loud if you can, in as much detail as you can. Tell me what's happening with this pool ball. And probably, if you overreach a little bit, actually, if you're a native English speaker and you overreach a little bit, you probably say that it's rolling from left to right. If you're actually a native Farsi or Arabic or Hebrew speaker, you might actually say that it's rolling from right to left, because that's just the way we read, and so that's the natural assumption. But the point I'd like to make is you have no idea. Without a really careful measurement, I don't know if this ball is rolling left to right or right to left. So in mechanics, we say there's no arrow of time. And every single solution that you ever came up with in mechanics was also okay if you erased the t and replaced it with negative t. So here's an example of something that would have been a little bit trickier, but you're not going to be fooled a second time. Is in this picture, you have no idea, now that you think about it, if the ball is being dropped and accelerating downwards at 9.81 meters per second squared. Could be 9.80, I don't know. Or if it's being thrown upwards with a big initial velocity and is accelerating downwards again at 9.81 meters per second, eventually coming to a stop here. So that's the arrow of time. Mechanics doesn't have one. Every solution that gave you, for instance, a parabola opening to the left was also an okay solution with the parabola basically tracing backwards. Okay, so here's the thermodynamic image. So here I have block A and block B. Clearly block A has a higher temperature. You know that from either looking at the temperature gauge or realizing that bigger speeds for these same blue molecule thingies mean larger kinetic energy. And it's going to be put in contact with block B, which clearly has lower temperature, lower average kinetic energy. They're brought together and they come to thermal equilibrium. So the hot block gets colder and the cold block gets hotter. Would you ever expect this process to go backwards? So I have these two purple blocks on the right, and spontaneously after bringing them together, I see block A get hotter and block B get colder. Absolutely not. So this idea of an arrow of time, this is the second law of thermodynamics. There are actually a few ways of phrasing the second law of thermodynamics. This is going to be the most non-technical and accessible, so we'll start with this one. It says exactly that heat can flow spontaneously from hot to cold. It cannot flow spontaneously from cold to hot. So this is something that probably shouldn't astonish you. F equals ma took 2,000 years to kind of figure out, because it's a little bit non-intuitive based on everyday experience. Not so much the second law of thermodynamics. So what it's really saying is you can't put a cold cup of coffee on a table and have it spontaneously become, scalding hot. Is that things will tend to equilibrate to that final shared temperature. Okay, so in the context of mechanics again, the only way that I know that this parabola is opening from right to left is because I know that there's a thermodynamic event at the end of it. Right? Without the pool and without the idea that all of these molecules are getting agitated and the temperature is going up. So cut off this picture there, this person could be doing an exotic trampoline trick. It's really the splash that lets me know. And what that is Avogadro's number of particles receiving a whole bunch of kinetic energy. And I'd never expect to see it backwards. So likewise, the only reason you know this mechanics picture is actually going from left to right is the loss of energy in each subsequent bounce, and that energy is being turned into thermal energy. So it's increasing the temperature of the molecules in the floor. So even when you can see this in mechanics, the idea of an arrow of time, it's intrinsically related to thermodynamics, i.e. friction. Okay, so we have two jobs in the remainder of this chapter, now that we've characterized heat as work. Heat and work in the first law of thermodynamics. One is to put some numbers on things, and secondly is to come up with useful ways of capitalizing on this. So heat engines are the idea that I just put a mechanical thing in front of spontaneous flow of heat from a hot source to a cold source, and somehow convince some of that heat energy to turn into work energy. So first law of thermodynamics and our discussions around that say that you can do this. And so now all I have to do is find a spontaneous flow from hot to cold and figure out how to do that, and I've got a heat engine. So this is a little bit how that would work in practice. We'll see some of these pictures, and they're a little bit too condensed. So how this might work for realsies is, let's say that I have some water, and I heat it up. I will turn that water into steam. If I turn a mole of water into a mole of steam, it goes from about the size of a sugar cube to 22 liters, which is like quite a big change in volume. So the steam expands. The expanding steam might turn a turbine. That turbine might generate some electricity, whatever I want to do with it, and then it'll go into a cold reservoir, condense back into that small amount of water, and then I can use it in a closed circuit to do something like this. So this is exactly that. So the hot stuff is going to flow, I'm going to extract some work from it, and then I'm going to have Q hot less the work that I extracted from it, and then I can turn the cycle again. So this is what a real heat engine might look like. And we'll go into some of the details and draw some PV diagrams for things like that. So overall, our goals, again, will be scientific and engineering. So we want to enumerate these laws. That was too many words for a law of physics for my taste. So I'd like to have this in terms of some quantity, and that will let us define entropy. So a scientific quantity on par with energy as a really useful thing to keep track of. And secondly, engineering goals, which would be to characterize how good these things are and, do the best we can to maximize the efficiency of heat engines, because, especially nowadays, we don't really want to be like too wasteful with energy. So the idea of efficiency of engines.